Hello engineers, it's Mr. Heller with the second video on our rotations section of work. Okay, today we're going to be talking about an idea of centripetal acceleration, and I'm going to illustrate what I mean by use of the fidget spinner again. So remember, when we turn the fidget spinner, if this is going at a constant rotation, okay, we can talk about the number of radians per second or the number of turns per second, number of turns per minute, and that might be constant. It's neither speeding up nor slowing down if the bearings are good enough. Okay, it might be slowing down slightly, but not appreciably. That's not what we mean by centripetal acceleration. Centripetal acceleration describes what's happening because even though the speed of this thing is constant, the velocity is changing. The velocity is positive as it goes in that direction and negative as it goes in that direction. Positive as it goes in that direction, negative as it goes in that direction. So we need some way of describing what's happening there. And our formula booklet gives us a couple of formulas to describe this. First of all, it says that the acceleration can be described as omega squared. Remember where omega is our angular velocity times the radius. That means that if two things have got the same angular velocity, a bigger radius is going to give us a bigger acceleration. The second formula tells us that if we know the straight line velocity, the linear velocity, we can do the linear velocity divided by r. So think about what that's going to feel like in a car. If I've got the same speed and I turn on a shorter radius, I'm going to feel more acceleration. A tighter curve with a shorter radius, it's going to feel like there's more acceleration. We're going to pull more G's, if you like. Okay, so let's have a look at how I'm going to apply those two formulas to some of this word examples. You'll recognise some of the numbers from the answers we got last week. Right, it says a fidget spinner has an angular velocity of 101 radians per second. The radius of the fidget spinner is 4 centimetres. So guess what? First thing I'm going to do, change that to 0.04 metres, just so that the units are going to be consistent. The centripetal acceleration of a point on the edge of the fidget spinner. Because I'm talking about an angular velocity, I'm going to be using A equals omega squared r, and then I can just pick up my numbers, say that A is 101 squared times 0.04. Then if I substitute that in using a calculator, I'm going to get this rather huge 408 meters per second squared. If you imagine sitting on a fidget spinner, that g-force that would be pulled if you were actually traveling like that would be phenomenal. Okay, so second question. A drill's got a radius of 3 millimeters. No surprises that I'm going to change that to 0.03 meters, and I've got this speed, half a meter per second roughly. Centripetal acceleration. This time I'm going to be using this formula, v squared over r, because I've got a linear velocity. I can tell it's a linear velocity because it's in meters per second. If it was kilometers per hour or meters per hour, that'd still be a linear velocity. Okay, and once again, I can pick up the values. Don't forget to square v in the formula, divide it by r, because my units are consistent. Don't need to change them at this stage. And that, if I've calculated correctly, it's going to come out at about 84.3 meters per second squared. Same unit for acceleration. And in fact, what I could do is I could change this value into a value of omega, and I'd get and then use this formula. I'd get exactly the same answer. Okay, so that's the straightforward use of this formula, use of that formula. Of course, as with all of these formulas, we can rearrange them. That's what I'm asked to do here. Car turns around a corner with a radius of 20 meters. Okay, great, still in constant, still in appropriate units there of meters already. And centripetal acceleration, 4 meters per second squared. And I want to know the linear speed of the car. Okay, so because I've got a linear speed that I'm trying to work out, the appropriate formula is going to be A equals v squared over r. But I'm going to rearrange before I start to give me v squared equals a times r, or v is equal to the square root of a times r. And then I can simply substitute in v is equal to the square root of 4 times 20, or square root of 80. And unsurprisingly, that's a decimal because 80 is not a square number. 80.94 meters per second. Now, if this wasn't an engineering context, I might be interested in converting this from meters per second to meters per hour, and then kilometers per hour, or even miles an hour. Because it's an engineering context, meters per second is perfectly fine to leave as a unit. Okay, now a test pilot can safely experience accelerations of about 70 meters per second squared. Now, if you remember that a G is about 10, roughly, meters per second squared, that's about 7G. So that's quite a hefty acceleration that this test pilot's going to be experiencing. A spinning rig with a radius of 12 meters, the maximum number of revolutions per minute. Well, I don't have a formula which links acceleration to revolutions per minute. That's radians per second, and that's meters per second. But this one's closer to revolutions per minute. So I'm going to use this formula. I'm going to say that A equals omega squared R, and then a little bit of rearranging tells me that omega squared is equal to A over R. So omega is a square root of A over R, substituting in and dividing and square rooting. Remember, it's all of this is square rooted. Let me just make sure that I remember all of that square rooted. Square root of A over R, and that's going to come out as about 2.415 radians per second. Now, I'm not rounding off at this stage. I've saved all that into my calculator. If it's that number of radians per second, I'm going to times it by 60 to work out the number of radians per minute, and that comes out at about 144.9 actually radians per minute. And then remember that because a full turn is 2 pi radians, I'm going to divide by 2 pi to get 23.1 revolutions per minute. Okay, I've rounded off to 3 significant figures there, but I've not rounded off here or here. Okay, so the worksheet, and in fact the exam that's coming up has got some questions on this. Same questions, roughly, different numbers to some of these. So good luck with those. Don't forget to email me if you've got any questions.